All right, guys, so in this first 8-1 video, what we're going to be doing is simplifying what we call rational expressions. A rational expression is essentially just a fraction. When we're dealing with expressions, though, it's obviously a little bit fancier than just like 2 over 3. You're going to have a whole expression divided by a whole separate expression. So rational is the fraction part. Expression is what means we're dealing with variables and different polynomial expressions. It's just that we have one polynomial expression in the numerator and a separate polynomial expression in the denominator. So when we are simplifying, picture if we had like 3 over 6 as a fraction and we had to reduce it down, what we would do is divide out common factors. When we're reducing expressions, you're doing the exact same thing. You're figuring out what those common factors are and then just reducing them down. All right, so if we look at example 1, our first example here, we are going to start by reducing that down. And the first thing that you will notice, it's kind of already factored down and ready to go. And so what we can do is see we've got a factor of y plus 7 and then divided by a factor of y plus 7. So since they have those same factors, y plus 7 divided by y plus 7 just reduces down to 1. So like this cancels out and just leaves us with a 1. Same thing here. So when we cancel those out, it's not that they're gone, they're not disappearing. It's just that y plus 7 divided by y plus 7 leaves us just with 1. All right, and the next thing we're going to do is look to see if anything can be factored down any further, and you can see the y squared minus 9. That can factor down further. All right, so it's not a prime expression because it can be broken down further than that. The 3y really can't. It's just 3 times y, and so we're just going to leave it exactly the way it is. But this y squared minus 9, it's the difference of squares, and we can factor that down as y plus 3, y minus 3. Okay, now that it's factored down, though, we can see that there really isn't anything that can cancel out. Be super careful with this. You can't take this y. It doesn't cancel with this y or this y. When you see a y plus 3, it's kind of a package deal. Unless the whole y plus 3 can cancel, just like this whole y plus 7 canceled, there's really nothing that you can do. You can't pick apart little bits and pieces of the factors to cancel. It's either all or nothing. And so the second part, it says, under what conditions is the expression defined? Things are defined as long as the denominator is not equal to 0. Okay, so anytime you see this, when they ask when the expression is defined, we know that the denominator cannot equal 0. Okay, so anything that would make the denominator equal to 0 would get cut out of our domain. Okay, so for us, what we're going to do is make sure that we can't plug in either of these things. So we know that y plus 3 can't equal 0. We also know that y minus 3 can't equal 0. So for both of these, just to get y by itself, we would subtract, and we've done this denominator restriction before. So we know that y can't equal negative 3, and then this one will tell us that y can't equal 3 either. So this expression is defined as long as y is not equal to plus or minus 3. Okay, so your final answer would look something like that. You reduce the expression down, but include any sort of domain restriction. We did this when we were dividing polynomials by polynomials. We would include a domain restriction. All right, so those are kind of the basics there. Example 2 is set up as a multiple choice option, kind of like a standardized test example. So this, it says, for what values is this expression undefined? So we're going to do what we did up here. We're going to set the denominator, say it cannot equal 0. So let's take p squared minus 2p minus 15 and recognize that it is not allowed to equal 0, otherwise our expression would be undefined. And so since this is a quadratic, we're going to factor it down. So start with p times p, that'll give us the p squared, and then whatever goes here times whatever goes here is supposed to multiply to negative 15, but our middle term should give us a negative 2. So these two numbers should multiply to negative 15 and add to negative 2. So that would be negative 5 and positive 3. So if we take these two different pieces and recognize that p minus 5 can't equal 0, nor can p plus 3 equal 0. If we add 5 to both sides here, we see that p can't equal 5. If we subtract 3 from both sides here, we see that p can't equal negative 3. All right, so 5 and negative 3 would be my two answers, and that would be option B. Okay, so that's the domain restriction that we've been talking about. The next thing we're going to look at here is just some more simplifying. We're doing the same sort of just like factoring and canceling, so we're going to get lots and lots of factor practice in. This example 3 is going to be the last one in video A, and it's just going to be a little trick where you can factor out -1. So we're going to start by factoring, but it's not going to look quite perfect. You'll see once we start factoring this down. So in both numerator and denominator here, what we're going to factor is what we call a GCF. So in the numerator, we've got a term right here and a term right here. Notice they both have an a to the 4th power. So we can start by factoring out a to the 4th power, and then in parentheses, we call these the leftovers. What would be left if we factored out an a to the 4th? So here, if we factored out an a to the 4th, we'd have a b left over. Here, if we factored out an a to the 4th, there would be a -2. Okay, so that's the factored version of my numerator, just getting out that GCF. And then divided by, now in the denominator, they both have an a cubed. Okay, so we've got an a cubed, and then in parentheses, when I factor out an a cubed, this leaves me with a 2 minus, and then when I factor out an a cubed, here I'm left with b. So first thing I want you to notice is these copies of a. When I have 4 copies in the numerator, 3 copies in the denominator, I can cancel out 3 copies. So here I'm just left with 1. When I cancel out 3 copies here, I'm left with 1 last copy of a. Okay, so I can do that first. And then look at the pieces that are in parentheses. They're almost identical, but they're actually perfect opposites of each other. All right, so this is a positive b and a -2, whereas this is a positive 2 and a negative b. So what I'm going to do is in the numerator, I'm going to factor out a negative. Okay, so I'm going to take out a negative and I'm going to attach it to this a. So I'm going to factor out a negative here, which would technically leave me with a negative b, and then factor out a negative here, which would leave me with a positive 2. And I'm just going to do that from one of the pieces, because then what should happen is the denominator should match. All right, so I just had a 1, which I don't need to write. You can if you want to. But so now this is -b plus 2, which is a different order, but it's exactly the same as 2 minus b. So now these can cancel out, because now they're exactly the same. So my reduced final answer would be a -a. So this and this are equivalent once I just reduce down all my common factors. So that's where we're going to end video A.